Hey guys, hope all is well. Today I'm going to try and walk you through a couple different things here. We're going to talk about delocalization of electrons on resonance structures, which sounds way harder than it is. And then we're going to talk about hybridized orbitals, something called molecular orbitals. You're familiar with atomic orbitals already. Those are s, p, d, f. Well, what we're going to see is that when a molecule is formed, those atomic orbitals don't work out. We need another solution in order for our molecules to make the shapes that they're going to make. So a reminder what we've already talked about. There's two big types of bonds. There's a sigma bond, and then there's a pi bond. A sigma bond is stronger, and it's the first bond that's formed. A sigma bond is formed by head-to-head overlap of those orbitals. So you can think of two orbitals that each have one electron from one atom. So this could be a hydrogen here, this could be a hydrogen there. Their orbitals are going to overlap, and each hydrogen is going to donate one electron to that sigma bond. And that's going to be a strong bond. The other type of bond we have is called a pi bond. A pi bond is a little bit weaker bond, and it's caused by additional bonds past that first bond. So it's going to be your double bond or your triple bond. And so what it's caused by is actually side-to-side overlap of orbitals, specifically of p orbitals. We'll learn here in a moment. And that side-to-side overlap causes a weaker bond to form, but it's an additional bond. Okay, so just to look real quick, we have a molecule here. And if we're going to count up the number of sigma and pi bonds, here we got a sigma, a sigma, a sigma. And then the first bond, this one right here, is also a sigma. And the first bond, that one right there, is a sigma. So remember, sigma bonds are your first bonds. They're the head-to-head overlap. So that molecule would have 5 sigma bonds. The additional bonds, though, are pi bonds. So there's 1 pi bond, 2 pi bonds, 3 pi bonds. So the triple bond actually has 2 pi bonds going on in there. All right, so that molecule right there is 5 sigma, 3 pi. So now what we're going to do is we're going to use those ideas of sigma and pi bonds to help us explain something we talked about earlier in this unit. We talked about resonance structures earlier in this unit. And remember, we said resonance structures are Lewis structures where you can actually move electrons or move bonds around and still get a valid structure, another valid structure. So for ozone, there's 2 major structures there. You can see the double bond could be between the first 2 oxygens, or it could be between the second 2 oxygens. So our first step in figuring out, what we're doing with these resonance structures would be to actually calculate the formal charge of each atom in each of the resonance structures to see if one structure was better than the other. But if you look at these 2 structures, you're going to see that they're going to be the exact same as far as formal charge goes, because they both have a single bonded pair of oxygen and a double bonded pair of oxygen. So their formal charges are going to be the same on either structure, so both structures are equally as valid. What that means, though, is not that ozone, O3, flips back and forth between those 2 structures. So instead, what's true is that the true structure is somewhere between those 2. So it's kind of like how a horse and a donkey are not going to produce a horse or a donkey offspring. They're going to produce an offspring that's a mule. It'd be pretty cool if they were able to produce an offspring that was at 1 minute a horse, and then the next minute you look back and it's a donkey. But unfortunately, that's not how it works. It makes a hybrid. So the satisfying or the actual explanation for this is that those extra electrons, the double bond electrons are actually spread out over all 3 oxygen atoms there. And the explanation for that is that the pi bond is actually able to delocalize, or the electrons involved in the pi bond are able to delocalize and actually spend time on all 3 oxygens there. And so what your actual structure would be something like this. Here's your oxygen atoms. They're going to have a single sigma. Ooh, my art's really good. So those are sigma bonds. But then they're also going to have pi bonds going on. And so here's your pi bonds. What's actually going to happen, those great green lines that I drew, are electrons swinging between all 3 oxygen atoms there. All right? And so that's called delocalization. So another example of that is a molecule called benzene. Benzene's a really famous molecule. It's a ring molecule. It looks like a hexagon. You can see it here in these 2 pictures. Benzene's actually got 6 carbons, obviously since it's a hexagon 6. And each of those carbons owns 1 double bond, or has 1 double bond between it. So you can see 2 double bonded carbons. Hold on, let me break out my pointer. Watch this, guys. Pretty cool, huh? So we got a double bond between these 2 carbons. Then you got a single bond. Then you got a double bond. Then you got a single bond. Then you got another double bond. Another single bond. Well, you could draw a resonance structure here, and you could flip where the double bond was. In other words, you can move. Oops, still on that pointer. Didn't mean to do that. You can move the double bond there, there, and there. And that would be your new resonance structure if you made those double bonds in those positions. So ultimately, what's actually the true structure of benzene is something where the double bond is actually delocalized over all 6 of the carbons. And so we can draw that out. And so you can see there, right here, is what benzene kind of looks like. Somewhere between a single bond and a double bond for each of those carbons. Well, what we can do is we can actually calculate something called bond order. And bond order is basically how strong is that bond. Is it a single bond? Is it a double bond? Is it somewhere in between? And so it's a really simple formula once you get the Lewis structure and the resonance structures drawn. And so we have a formula for bond order. I wrote BO. Not what the person next to you has, but bond order. Bond order is the total number of bonds over the number of bonding domains. And if you remember, a bonding domain means basically this counts as 1 domain, that counts as 1 domain, this counts as 1 domain. It's just like what we were talking about when we were doing our VSEPR or molecular geometry stuff. So I'm going to kind of skip a couple steps here and draw out PO4 3- for you. That's its Lewis structure, or its best Lewis structures. You could draw 4 resonance structures here. You can move the double bond to any of those 4 oxygens, or any of the 3 other oxygens, other than the picture we have drawn. So if we were going to try and calculate the bond order, we got to calculate first the total number of bonds. So 1, 2, 3, 4, 5 total bonds. And then we put that over the number of bonding domains around the center atom. So 1, 2, 3, 4. And so the bond order for PO4 there would be 5/4 or 1 1/4 bond, 1.25. So that means in reality, the strength of those bonds is not a single bond strength and it's not a double bond strength. It's like